Okay.
Okay, so welcome everyone to the One Pinsky's seminar. For those of you who are not aware, the talk will be given in English. Part of our collaborators, Peter Vanya, is joining us from the Czech Republic, who I think is suffering from COVID just as much as we are these days. This is part of the one's work towards his master thesis. It relies on a paper that was just accepted 2 days ago to robotics and automation letter, so we're super excited about that. And Doan is going to describe his work. The talk is going to be an hour where we're going to leave about 10 minutes at the end for questions. I suggest to refrain from asking questions during the talk unless something is not clear. But if it's something to open a discussion, then let's leave that to the end. And with that, I'm super excited to pass Doron the virtual baton and to hear about his work.
Thanks, Oren. Thanks everyone who joined us. So today I'm gonna talk about my master research thesis, and the talk's called T-star epsilon bounded suboptimal efficient motion planning for minimum time planar curvature constraint system. And this work was under the supervision of Professor Oren Zaltzman. And as Oren mentioned, paper with the same name, just accepted to robotics and automation letters. We will start with a short introduction or explanation of what planar curvature constraints are and in what domain we aim to solve the motion planning problem. So planar curvature constraint systems are systems who must follow some radius when they turn, and those systems can be car or forklift, any vehicle to be practically, or surgical needle, cerebral needle. Those systems are defined by 3 degrees of freedom: the position, the planar position, and XY, and the heading angle or orientation. Motion planning for those systems can be includes in a variety of applications such as autonomous cars or surgical robots. Unfortunately, it is already been shown that even determining if a collision-free path for the motion planning problem is NP hard, even for the planar situation. So this problem of motion planning is pretty hard. Usually the problem can be solved using a sampling based method, as we can see example here. Or the space can be discretized to a grid, and then the motion planning problem can be solved using search based method. Interestingly, in both approaches, the most expensive, computationally expensive part, or the computational bottleneck, is to compute the transition between the system configuration. As we can see here, the line between the dots, or in the discrete space, the line who connects two neighbors' cells. Our work focused on the discrete space problem. Now we're gonna give a short background about work have been done in this region. So Dubin solved the problem of find optimal path planar system at a single speed, which is the shortest path. The inputs are the start and goal configuration and the turning radius the system must follow, and the output is the shortest path. In the scenario, the vehicle can move at constant velocity. The time optimal and the shortest are identical. Dubins found there are only just 6 options to be optimal of those conditions. Four of them, including a turning segment denoted as R and left for right and left respectively, and the rest two, including three turning segment. The first four, sorry, including also a straight segment, which denoted as S. Dubin's paths are in common use since they have an analytical solution and they are easy and fast to compute. Unfortunately, Dubins allow the system, as I mentioned, to move only at constant speed. So Wallach et al. Researched the problem of time-optimal transitions between two configurations for variable speed system with unbounded acceleration when the speed can be alternated instantly in the free space, which means without obstacles. In those settings, only two speed need to be considered: the maximum speed for allow fast progress and the minimum speed for allow better maneuverability. As we can see here in the figure, in those conditions or when the system can change its velocity, the shortest path or Dubins and the time optimal are not longer identical. The two main differences between Dubin's model and the variable speed model are that in the variable speed model, there are 34 candidates, as we can see here in the table, instead of the 6 in Dubin's. And more important, those candidates are evaluated by numerical optimization, which is expensive, computationally expensive operation. Song et al. Took the approach of Wallach and developed an algorithm called T-star that find time optimal path in discrete space with obstacles, as we can see here in the figure. Since the space is discrete, for a given number of neighbor cells and numbers of orientation in each cell, there are a finite number of optional transitions from any configuration. So T-star computes all the time optimal transitions, hopefully offline if it's possible, and then it runs A-star like search for finding the time optimal path. The computations of time optimal transitions are very demanding and cannot be done pre-processing in all scenarios. And our work starts with that point of implementing T-star, and when we implement it, we noticed a few things, and this has led us to our key insight of our work. So our key insights are that the computing all the time optimal transitions lasts much more time, or 2 orders of magnitude more than any other algorithmic component. What even interesting is most of the computed transitions are unnecessary in many cases, which means only a small fraction of all possible transitions are used to be part of the found solution by T-star. So we believe that if we can compute only the necessary time optimal transitions for the solution, so that way we can save a large amount of time, computational time. And as we will see, our algorithm T-star epsilon can run faster than T-star up to an average factor of 40 with still provide guarantees on the quality of the solution. Now I will review works that try as well to reduce this computational effort and solve the motion planning problem when offline computation of all possible transition cannot be done. To reduce computational effort, Wilson et al. Developed a multi-speed Dubin's model. In the proposed model, the system moved like Dubin's path, but each one of the three segments in Dubin's path can be in different speed. That way, they try to use both the analytical solution from Dubin's, which is very cheap and easy to compute, and the better maneuverability that the multi-speed model allows. The model implemented in the first paper in discrete space, and compared to Dubin's and T-star, or they call it Wallach, but it's the same model and their model. And in other work of the same group, they use this approach of multi-speed Dubin's for motion planning of planar curvature constraint system in continuous space, where there is no finite number of transitions, and of course those transitions cannot be computed in advance. For the presented experiment, the found path was not far from the optimal, but there are no guarantees regarding this quality of or how far from the optimal the found solution will be. Another scenario when all-time optimal transition cannot be computed in advance is a scenario where there are dynamic environment conditions such as wind or ocean currents. In those conditions, Dubin's path can be computed similarly as described. However, only 2 of Dubin's candidates have an analytical solution, and the rest 4, and to compute the rest 4, a root find problem must to be solved, and this is computationally expensive operation. Mittal and all solved this problem of motion planning, fast motion planning for planar curvature constraint system under ocean current, and to do so they used only 2 candidates, those with the analytical solution, and they developed an online planner. However, the planner does not take into account the quality or the solution cost of the found path, and just focused on the running time. Now we're gonna go over some definitions about our model. So this is our kinematic model with a 3 dynamic degree of freedom, sorry. The position and the orientation. U here is the turning rate, or if we are drivers of a car, let's say, it's how much we turning the steering wheel. Since the variable speed model with unbounded acceleration, only the extreme speed need to be considered, the minimum and the maximum. We will also have just 2 turning radii, rho max and rho min, for the turning with the maximum and the minimum speed respectively. An admissible path gamma is path that include collision free cells from start to goal configurations, as we can see here in the figures. In our model, the objective function that we want to minimize is time, and the cost function is stepwise cost between neighboring configurations in the path, and the cost path gamma is depending on the speed of the vehicle during a path segment d tau, as we can see here. So given we get paths that connect between start and goal configuration, path gamma is considered to be optimal if there is no other gamma prime with smaller cost, and gamma is called bounded suboptimal for some approximation factor epsilon, which is equal or greater than 0. If for any other gamma prime, the cost of gamma is less than 1 plus epsilon times cost of gamma prime. In our work, we are focused on the bounded suboptimal, finding the bounded suboptimal path. Our algorithm aims to reduce computational effort and hence running time, while providing guarantees regarding the quality of the found solution. It is inspired by two known algorithms, A star epsilon's search algorithm and T star, the optimal algorithm for motion planning of planar curvature constraint system with variable speed. So in the next slide, I will describe those two in detail. So A star epsilon is a bounded suboptimal version of the well-known A star search algorithm. When during the search, A star expands the node with the smallest value of f in the priority queue called open list, which the f cost is sum of the cost to come from the source G, and estimation of cost to go to the goal H. And here we can see a demonstration of A star algorithm. In any step, it expands the node with the smallest f value. In contrary, A star epsilon build a focal list that include all the nodes in the open, that their f cost is at most 1 plus epsilon, the cost of the node with the smallest f cost in the open. And it is proved that for any expansion of nodes from the focal list, the cost of the path found by A star epsilon is bounded by 1 plus epsilon of the optimal cost for any choose of epsilon. And as we can see here, A star epsilon find solution faster than A star, and for our example, epsilon is 0.1, which means the cost is found by 22 is exactly 10% more the optimal. So the time, since the time optimal transitions are the most most computationally expensive component of T star, and our algorithm T star epsilon aim to reduce this effort by reducing the number of time optimal transitions computations. Now I will explain those transitions in detail. So let denote the set of all possible transition in calligraphy capital T. And in the setting of 8 connected grid or 8 neighbors for each cell, and in each cell there are 8 possible orientations. There are total of 512 transitions. However, this number can be reduced. For example, we can see how in this grid and this grid, what with different starting orientation, the transition are just the same. So we can see that each any transition here can be expressed by just the rotation of the same transition here, and all it works also for all the other starting orientation, and also for the lower row. So we left only with two optional starting orientation, but also we can apply symmetry about the starting orientation. And we can see here, for example, that this transition from here to here and this transition here to here are just the same, and we can see it but by like this. And also we can apply the same idea here, and the rotation symmetry, sorry, about the starting orientation, and find those transitions are the same, and we left from 512 which with just 68 possible transitions. So T-star algorithm, now we will see how T-star algorithm is working. First is compute, hopefully offline, all the time optimal transition using the table of the 34 candidates. Then you get the instance or the map, the start and goal configuration, and then it ran a star like search. We can see that T-star used only small fraction of the all possible, or the all computed actually transitions. And here we can see another example of the rotation of, or how those transitions can be seen here. So after an extensive evaluation, we found that, of course, only small fraction of all possible time optimal transition makes up the optimal path found by T-star, as we saw in the previous slide, and that the path found by minimum speed Dubin's path for the same start and goal configuration and the T-star are share large portion of the solution transition. Here in this show example, we can see the solution of T-star and the Dubins with minimum speed, and we can see that they are share large portion. And to be specific, all the transitions who appeared in the minimum speed Dubins are also used in the T-star solution. And here we can see not just one example, but it's this conclusion is also holds for many tested we will run. And now I will describe our algorithm T-star epsilon. So the algorithm has three main components. First, we assume we can compute a lower bound for the true cost of transition, and we assume we can compute it efficiently. We use A star epsilon like search instead of A star like search in T-star algorithm for find bounded suboptimal instead of optimal. And based on Dubins with minimum speed, we have an idea about which transitions have high probability to be part of found path. The first two components are related to the bounded suboptimal solution, and the third one is some kind of heuristic of initial set of computed transition. After we understood that the computations of time optimal transitions are the most computationally expensive component, and in many cases unnecessary, we aim to reduce this effort. As T-star computes all the transition and store them, any computed transition can be stored and reused with no expensive evaluation computation. So T-star epsilon aim to reuse already computed time optimal transition while assuring the bounded suboptimal solution. We denote the true cost of a transition, as we already see, as C, and a lower bound for the true cost as C hat, and for any transition, the cost of the lower bound of a transition is less or equal the true cost. In addition, we have an indicator function, and we denote it with kappa, that indicate if a given transition has already been computed or not. Since T star epsilon aims to reduce the number of time optimal transitions computation by reuse of already computed transitions, it prioritized nodes that the true cost of their transition was already computed. In this slide, we will see how those nodes are prioritized. For any node, its G cost, or cost to come from the source, can be expressed as the sum of the G cost of node's parent and the cost from the cost of the transition between the parent and the node itself, which can be true cost or a lower bound. Here we can see an example how those parents-child relation look on a grid. So this, for example, a parent, this is one of his child, another, and of course, those not all his child, but each transition of those can be a true cost or a lower bound for the true cost. So T star epsilon use a focal list to decide which node to expand during the search. So let's assume at some point we have this set of computed and not computed transitions. And let's assume that our approximation factor is equal to 0.3. The open list in that point, for example, the open list is sorted by the F value of the nodes, and we will build a focal list that for all nodes with 1 plus epsilon F cost of the nodes in the top of the open list. And for example, if we got a 0.3 epsilon, so that means that if the minimum F cost is 10, so all the nodes with up to 13 F cost will be included in the focal list. And when we have the focal list, we can choose a node for expansion as we want and still provide guarantees regarding the quality of the solution. Since we want to reuse as we can already computed transitions, we prioritize nodes with already computed transitions, and we prioritize first all those nodes, and just after that we sort the focal list by the F value. And now we will see how T star epsilon is working. First, it gets the instance, the start and goal in the map. It finds the shortest path using Dubin's minimum speed. It computes all the transitions who appeared in Dubin's path at minimum speed. It computes those transitions through cost. And from that point, he ran a star epsilon like search and prioritized to expand nodes with transitions between them that the time optimal or the true cost was has been already computed. If it's necessary, it's computing more transitions, and in the end, it finds a bounded suboptimal solution. Now we will move forward for the evaluations of T star epsilon. So we start with the setting of our experiment. We randomly generate 10 maps, each of them covered by 25% of obstacles, and ran 100 experiment with randomly start and goal configuration. First, we want to validate that the component we added to the algorithm are really beneficial. So we ran T star epsilon with and without the first finding the minimum speed Dubin's solution. And we can see that the average number of computed time optimal transitions, or call to the function who computed the true cost of transition C, is less than the T star epsilon without running this two component of minimum speed Dubins. And what we can also see that in large value of epsilon, the number of computed the number of computed transitions are converged to the number of transitions who appeared in the minimum speed Dubin's solution. Then we examine several options for a lower bound for the true cost of the transitions. A lower bound must be optimistic, which means its cost must be smaller than the true cost to be, of course, a lower bound. It needs also to be informative, which means it should be close as possible to the true cost. And finally, it must be cheap to compute, since its main purpose is to reduce computationally effort. So we examined three options for lower bound: Euclidean distance between nodes, Dubin's path without obstacles, without considering the obstacles between two cells, and Dubin's path with obstacles, which is the most informative, but also required a collision detection expensive operation. And we see that in some cases its runtime more than the Dubins without obstacles, and we found that Dubins without accounting obstacles balance well between how informative it is and how easy to compute it is. So now we will moving forward to see a comparison between T star and T star epsilon. As we can see, T star epsilon finds a solution with average cost that's much closer to the optimal than it allowed. For example, for epsilon equal to 3, the upper bound of the solution is 4 times the optimal, but T star epsilon finds a solution with an average cost of higher just by 10% than the optimal. However, if T star can compute all the time optimal solution in pre-processing phase, it finds the solution faster and better than T star, because the running of T star on online includes just this small component. Here we have a logarithmic scale. But if we are counting the offline computation of T star epsilon speed up the running time significantly. As we saw in the related work section, offline computation of all time optimal transition cannot be done in all scenarios. In those scenarios, the use of T star epsilon can be beneficial, and in the next slide, we will see an example of such scenario. We choose to demonstrate our approach when there is a wind field that is additive to the velocity. In those conditions, the time optimal transition cannot be computed in offline step and must be computed during the run of the algorithm. We, of course, updated the kinematic model to take into account the wind. And in those conditions, T star working a bit different. It starts with get the instance, which now includes not only the start and go location, but also the wind condition that affects the kinematic model. After that, it computes all the time optimal transitions, and then it run a star like search and find the time optimal path under the given wind conditions. Here we can see here in the figure an example of how challenging motion planning under wind can be. And we evaluated T star and T star epsilon average over 1,000 experiments with different wind condition. And notice that the average solution is farther from the optimal than where was no wind. However, the speed up of the running time is significant and can by up to by a factor of 30, an average factor of 35 times faster than T star. So to summarize, our developed algorithm can reduce the running time and still give guarantees regarding the quality of the found solution. And for the best of our knowledge, this was never done before. Regarding future work, we can consider a lifelong version when the search never ends and the system is given new goal when it's reached. In those settings, the wind condition can be changed from query to query, and online computing all the transition is not anymore practical. Another real life setting can be include a situation that we cannot define in advance the approximation factor epsilon. In this setting, we can define an upper bound of the running time instead of the solution and we will start with a significant large value of epsilon and decrease it as long as we left a time. Here we can see a very first result of our implementation of anytime version of algorithm T star epsilon. And I want to thank to my supervisor, Professor Oner Zaltzman, and our colleague, Professor Jan Feigl and Mr. Peter Vana from the Czech Technical University of Prague. And now I assume I take some questions.
Thank you, Doron. There was a mini discussion on the units, on how you defined a cost function in the chat. I think that one is a bit technical, and it would be nice if you can look into that either after the questions, if we have time, or offline. But I would like to open it up to conceptual questions about the approach, if anyone in the audience has any. Okay. So maybe since we do have time, Elon, maybe do you want to ask the question out loud so we can solve the issue?
Sure. First of all, it was a great talk. Thank you very much. It is only my problem, I am sure. The cost function of total travel time, you stated it is the integral of 1 over speed times dt. Probably it's my problem, just running through the math. So it's like the second slide, maybe third slide, or
I find it, yeah.
You called it, I don't know, like C of gamma.
Yeah, it's I just start with, it's not dt, it's d tau, which is path segment in meters. And
it's path length. It's like ds.
Yeah, it's path segment.
Oh, I'm sorry. No, it's perfect.
It's
path length is perfect. It ends up as seconds.
Yeah, the units are.
Yeah, perfect. So if there is any time, maybe you can explain again. Look, the key issue in all your work are the T star transitions. So they compute all possible transitions, which are, I assume, time optimal, correct?
Yeah.
Okay, and you said like 512 or something like that.
Yeah.
So can you explain, when you have time optimal transition, it was the key point, in my opinion, in your lecture or seminar, you have 512 time optimal transition between neighboring cells. How do you do the reduction?
So I have
into 68 possibilities.
Yeah, let's see here. This is this slide.
Thank you.
This is 512 is for a given setting of 8 cells neighbors and 8 orientation on each cell. We got just 8 of the power of 3. This go to 512 because it's 8 orientation for the start and orientation for the goal and 8 neighbor cells. So we can see clearly that this transition from that starting orientation in this cell here or here to here is just the same. The only difference between them is the rotation about with 90 degree, right?
Yes.
Okay, so we can express all the same. We can express all the transitions here just by rotating by 90 degree this starting transitions orientation, sorry, and here is 180 and here is 270. Okay. And it works also for this row. So we left only with those two starting orientation. Okay, and this is we applied until now rotation. Now we can use also symmetry, and how the symmetry about the starting orientation look like is, for example, the transition from here to here and from here to here is just the same, and we can apply also about the starting orientation for this set of transitions, and we can see that the transition from here to here and here from here to here just also the same, and we left with 68 because those 4 and 4 here are not rotated. So this is maybe works the 68 and not some other power of 2 or something like this. But we left with 68 transitions who covered all the possible transitions in the setting.
Okay, yeah, really cool. Yeah, thank you.
Welcome.
Any more questions? Thanks, Elon, for joining the talk. Okay, so we can finish early. Thanks to Juan for the presentation. Thank you all for joining.
Thank you very much for joining us.
And Shabbat Shalom to everyone.
Thank you. Shabbat Shalom.
Bye. Thank you.